the limit comparison test works very nicely when you have a fraction that is algebraic in nature, and we would like to compare the fraction to something a lot simpler. Think about the same way we deal with the limit as n goes to infinity. We're talking about horizontal asymptotes. We only look at the most significant terms. So on the top, we don't have any term except for the constant. On the bottom, we've got this 3n squared as the most significant term. So I'm going to go ahead and compare this series to 1 over n squared. You could use 3n squared. There's no real point. Either way, it's going to work out the same either way. The trick is to make sure that you pick something that matches the degree of the original. So we're going to compare our original to this, which well, this is a p series, right? So p series where p equals, I'm waiting for you guys to tell me. I'm waiting for someone to tell me. Oh, right, okay, yeah, thank you. It's p equals 2, which is, the important thing about 2 is it's, right, exactly, greater than 1, yes, which implies that this, what is it? Oh, right, it converges. Okay, so if we can do the limit comparison test and do that limit of the ratio of the terms and get a finite and positive value, then we're cooking. We're going to go ahead and take the limit as n approaches infinity, and we'll put, it doesn't matter which one you put on top. I'll put this one on top and this one on bottom. And we know that this is going to simplify. We're dividing by the fraction, which means we're multiplying by the reciprocal. So the denominator of the denominator becomes the numerator. And then that n squared goes on the bottom. And look at that. We've got the same degree on the top and the bottom. That's because we picked this. We knew that was going to cause this to happen. And so we only look at the most significant terms, and we get 3n squared over n squared, which reduces to 3, which is positive and finite. Okay? Therefore, because that limit is positive and finite, we can conclude that the original series does the same thing as the compared series. In other words, in this case, it converges. Converges by the limit comparison tests. All right. Think about what would have happened if we changed this to, we put a 3 in here instead. Then we'd have a 3 in here, and we'd have a 3 in here, and it would be 3 over 3, which would be 1. Okay? Still positive and finite. So you can keep that leading coefficient there if you'd like, but it might be just a little bit simpler to not worry about it. Either way. All right. So along the same lines, we're going to go ahead and say, oh, this is a lot like 1 over the square root of n. Right? We don't really care what this number is. We definitely don't care what this number is because that's a constant. This scalar factor also doesn't really matter because it's not going to change a positive finite value to something other than a positive finite value. And again, this is a p series. This thing is going to diverge because the p series tells us that if p is 1/2, or anything in fact that is less than or equal to 1, then the series will diverge. So we'll now use the limit comparison test. We'll take the limit as n approaches infinity of, put either one of them on the top, put the other one on the bottom. And you're going to start seeing a lot of similarities here between these problems. You're going to feel like you're doing the same thing over and over again. And this is the same thing as the square root of 3. Right? Ignore the -2, then things reduce down to the square root of 3, which is positive and finite. Positive and finite, which is the prerequisite for coming to the conclusion that the original series does the same thing as the compared series. In this case, the compared series diverges, so this one also diverges by the limit comparison test. So remember, with all of these comparison tests, I said this before, but I'll mention it again, we're always going to compare it, obviously, to a known series, And we have to talk about what we know about that known series. So we're using a different test for that one, and then because of that different test, we can use the limit comparison test. So these comparison tests really do require two different tests. All right, so this is the last one on this row. It gets a little bit more complicated because the numerator is not 1, but we're going to focus on the most significant term at the top, most significant term on the bottom, and n squared over n to the 5th reduces to 1 over n cubed. So that's going to be the series that we're going to compare. Okay, so we know that this is a p-series that converges because the p-series tells us that any p-value, in this case 3, that is greater than 1 is going to converge. So we can try the limit comparison test by taking the limit of the corresponding terms. And this one, again, will be a little bit more complicated, but we can do it. I have faith in us. We're dividing by that fraction, which means we're multiplying by its reciprocal. So the 4n to the 5th plus n cubed goes in the numerator, and the n to the 3rd gets multiplied by the n squared minus 10. Okay, the most significant term on the top is the 4n to the 5th. The most significant term on the bottom is the 1n to the 5th. So the rest of it goes away, and we have 4 divided by 1, which is 4, which is obviously finite and positive. Therefore, we can conclude that the original series does the same thing as the compared series. It converges by the limit comparison test. All right, cool. So if we look at these other examples, kind of more of the same, I think. They might get a little bit more complicated. Again, we're going to focus on the most significant term on the top and the bottom. The square root of n over n squared reduces down to 1 over n raised to the 3/2. Okay, so we're going to compare this to the sum of this fraction. And what does this do? This is another p-series. So the p-series says that this one converges because p-series test goes like this. If the p-value of 3 over 2 is greater than 1, then our series converges. So now that we know how that one works, we can compare using the limit comparison test. And we'll take 1 over n to the 3/2 divided by, I'll write it as n to the 1/2 over n squared plus 1. No need to mix radicals and rational exponents, just pick one or the other. And this is going to be n squared plus 1 on the top, and n to the 3/2 times n to the 1/2 on the bottom, which is just n squared. So we have n squared plus 1 over n squared. That approaches 1, which is positive and finite. Therefore, whatever the compared series does, the original series does as well. In this case, converges. Therefore, the series root n over n squared plus 1 converges by the limit comparison test. All right. This one's going to be a little bit trickier because we've got this exponential expression. Anyone have any ideas? Well, notice in the instructions that it doesn't actually say to use the limit comparison test. Determine the convergence or divergence of the series. Why not go back to the very first thing we should always ask? What happens to the limit of the nth term? This is definitely an infinity over infinity, but what sort of infinity over infinity? We've got n, which is linear, times 2 to the n, which is exponential on the top. Linear times exponential is pretty big. In fact, even if that n weren't there, if it was just the exponential, that's going to beat this n cubed any day of the week. Exponential is always bigger than cubic, right? Think about that hierarchy of infinities. So if the bigger one is on the top, oh gosh, That's infinity. We're done. We could just conclude that the series, I don't want to rewrite the whole series, so I'll just say series, diverges by what? It was that third test that we learned, by the nth term test for divergence, right? Because this is not equal to 0. Okay, that's the only time the nth term test is not usable, is if the limit equals 0. If the limit does equal 0, then don't use the nth term test. We have to do something else. All right, back to straight up polynomials. This is fairly nice because we can just look at the most significant term on the top and the most significant term on the bottom. Again, we don't really care about that 4 so much. And n to the 4th over n to the 5th is the same thing as 1 over n. This is going to be the harmonic series, so we expect that this thing is going to converge just like the harmonic series. All right, so we already know the answer. If it's multiple choice and you don't have to show your work, you're done. Diverges, end of story. Or diverges by the limit comparison test, end of story. But if we're going to show our work, then it'll look exactly the same way as all the others. We're going to look at the sum of 1 over n, which diverges either by p series or by the simple harmonic series. Again, this is, you could call this an extra 11th test. We haven't done all the other 10, but this doesn't count as one of the 10 tests. This is just one that we have memorized. And if you don't like to use an 11th test, then you can use the p series, because p equals 1, which is less than or equal to 1. All right, so anyway, now that we know how this behaves, we can look at the limit comparison test, which has us looking at the ratio of corresponding terms. And we already know what's going to happen, right? We've got the 4n to the 5th minus n cubed plus 7 on the top. We've got the n and the n to the 4th plus 10 on the bottom. Oh, offensive notation. What did I forget? All right, I forgot the limit here, right? We want to make sure that we always include the limit. The limit doesn't equal that fraction. The limit equals the limit of that fraction. Anyway, n to the 5th on the top. This is a 4n to the 5th on the top. This is 1n to the 5th on the bottom when we distribute, so that's going to be 4. And 4 is positive and finite. So that means that whatever this does. So since this one diverges, we can conclude, therefore, the original series, which is n to the 4th plus 10 over 4, n to the 5th minus n cubed plus 3, also diverges. This one by the limit comparison test.